Now have a look at here. Now I'm going to explain you the variations of this equation. Now the variation, what is the variation? The main thing you have to learn is how the pressure exert. That is given in the previous video. But and the next one is how the kinetic energy of each molecule and the energy in total gas sample in various methods. Not in a single way, there are multiple methods. For this equation, the pressure-wise and energy-wise behavior that we are going to study here. Okay, to get the energy, there are two ways. One is very simple and direct method. Other one is multiple steps, but you finally come to this step. What? E equals to 3/2 K T for one molecule. Then you might think, sir, why do we need to learn the long method? It is just imagine in Hess cycle in chemistry, it finally says like the initial energy and final energy difference is relevant of the path. So you may have to sometimes spend multiple steps to bring the result to here, right? So you may have to learn everything that comes, especially in MCQs, but in other areas as well. It is very important. Firstly, I teach you in the long method. Then finally, I will teach you the short method. There are two ways. Okay, let's see how it is. Okay, according to the first video, you may have seen the molecules are moving in random directions, in random velocities, having a mass of m and moving with velocity of v. Now I'm going to express this in kinetic, in terms of kinetic energy. E here equals to what? Half mv square. Now generally it is for certain molecule, but randomly all the molecules are moving in random velocities. I took an average of the mean velocity, that is c bar. When I substitute this to here, your equation just becomes half mc square bar. Okay. This is the magic. This is the magic. This is the equation x, what I have. Let's see the other equations. So all the time you have to plug everything to here. That's the stuff. Okay, have a look at here. Now the number one. What I'm going to do? Okay, number one, the long method. Okay, long method. Universal gas equation PV equals to nRT. This is the most important one. And the number of moles equals to mass of the sample over molar mass. Here we took the mass of this one as the mass of a molecule. What? Mass of a molecule. See, I have explained this in the previous video, but this is the number of molecules. Number of molecules. Number of molecules. Okay. The c square bar is the root mean square velocity. VRM is. I have thoroughly explained that in the previous video. Now, number of moles equals to mass of the gas sample. So let's consider that gas sample we had. This gas sample has number of molecules, number of moles, and the universal gas constant, having some volume, right? Having some volume, and the mass of the molecule, and the VRMS, or just C bar. And each molecule have kinetic energy, kinetic, and the total kinetic energy. We have to find all of these variables. Don't be panic. I'll teach you one by one. Number of moles or molar mass. Okay. Number of moles multiplied by Avogadro's constant. Sometimes from the same equation you can derive like N over L. Okay. And this mass is mass of the sample. This is the M naught as I mark here. Mass of the whole sample is mass of a one molecule multiplied by number of molecules. And molar mass is mass of a one molecule multiplied by Avogadro's constant. Right. These variables you will have to know. Right. Now I'm going to get one equation, so I will mark it like equation 1 for my convenience. Now I'm going to get this equation as equation 2. Equation 2, equation 3, equation 4, equation 5, equation 6, equation 7. Like helping equations 2. Now I'm going to plug, this one is my x factor, sorry. This one is my x factor, the equation x. Now see, equation number 1 from here, for the PV part of the same equation here, the other equation here, PV part, I'm going to plug with this one. Right, let's see. Into equation x. Right, substitution. The whole PV part is going to substituted by this. nRT over equals to 1 over 3 mn c square bar. Right. To this equation, this is my equation, another junction. It is a Y junction. Okay. That's why I took the equation as Y junction. Right. Okay. Here, you start from a point where it is X. You will reach to a Y junction. It just turns to another direction, and you finally come to your destination Z. But here, sometimes you may have to go to Y1 and Y2 and finally comes to here. I will firstly take the first path and experience that and finally go in the second path as well. Okay. Now I'm going to choose first path, the longest path. Here I will only try to get the C square bar from here. My aim is to get the C square bar. Firstly, I'm going to get C square subjected. NR3 NRT divided by M N. Right, okay. Now this is what my equation is. Another junction. Another junction. I will consider it like Y1. Y1 my junction, one of my junction. Right. Can you see M is a mass of one molecule multiplied by mass of all molecules in the sample. Is there anything? Yes. M into N is none other than M naught. M naught. M naught. M naught means the mass of the gas sample altogether. Okay. Now I am going to extend it like this way. 3 nRT over M naught. I'm going to separate this part now. I'm going to separate. Now see N over M. I know another thing. M over capital M equals to N. Right? See, from the equation 3, from the equation number 3, from equation number 3. How will we look at? I have the ratio of N over M from the equation number 3, N over M naught. N over M naught is none other than 1 over capital M. It is the derivation of the equation number 3, that is equation number 3 dash. Okay, I'm going to substitute this whole thing by 1 over capital M. Now my equation just become 3 RP over capital M. This is a very, very, very important point in the journey. See, 3 RP over capital M. This is one of the very important junction here. I will mark it like Y2. Very important junction. Okay. Good after. Very, very important junction here. Right. I'm still in the process. Okay. Now pause the video and copy everything, whatever you want. That's how you should learn in a video class. Okay. Now I'm pretty sure you paused and wrote everything. Now let's move forward. Now my aim is to find out the kinetic energy. Now my aim is mainly to join this C bar square to here. C bar square to here. Okay. I will erase this area only by keeping this y as my reference. Right. Now I just need to plug it to here. Okay, how will you do that? Ek is equals to 1 over 2 m in a bracket square root of 3RT over capital M and square it. When you square anything like this, square root of 2 and you square it. So what happens? Let's see. Square root of 2 multiplied by square root of 2 finally becomes 2. Like that, root sign cancel off. Right? O-level mathematics. Now, Ek equals to half m. So not half now. This sorry, I will write like half m 3RT over capital M. So you can write like what? You can bring this 3 front 3 over 2 m over capital M RT. RT. This M stands for a mass of a single molecule. This capital M stands for mass of a what? Molar mass. Molar mass. Molar mass. Okay. See, molar mass and this one has a certain relationship that is from the equation number 7. From 7. Okay. From 7. From 7. From 7. M over M is, see, M over M is none other than 1 over capital L. Now I'm going to substitute it to here. And you will see the magic here. This whole term I'm going to replace with this. Ak is equals to 3 over 2 RT over L. R right. So this is a universal gas law. Universal gas constant. Sorry, R is R. Again, R is universal gas constant 8.314 J mole minus 1 K minus 1. Equation, helping equation. That is equation. Did I use 8 here? Okay, no problem. It is equation 8. Right? L is the Avogadro's constant. I take it like 6, because decimal negligible. Mole minus 1 per mole. When you divide these two, you can get another constant that is called what? R over L, that we call Boltzmann constant. It is 1.38 into 10 to the power minus 23 J K minus 1. That is equation 9, something like that. So this is known as Boltzmann's constant. Which one? R over L. Now I'm going to substitute and get my first result. It is 3 over 2 KT. You can see now the kinetic energy of a molecule is completely depending on with only one factor. What? Temperature, because this is 3 over 2 is a constant. Boltzmann constant is also a constant. Whether it is hydrogen, whether it is oxygen, whether it's carbon dioxide, big molecule, or water molecule, or like big gas molecule like propane, butane. It doesn't matter which molecule it is. If it is a ideal gas molecule, there are no ideal things, but assumed to be ideal gas molecule. Under large temperatures, all the molecules act as if ideal. Keep that in remember as well. Whether it is hydrogen or helium, helium is 4 times heavier than hydrogen. If it's 2 molecules, it is 2 times heavier than, but doesn't matter. If the temperature is the same, all the molecules have same kinetic energy. Keep that in mind for MCQ purpose. Right. This is what the first result and final most result I want from one of the way, longest way. There are big junctions, and now you finally came to the final destination. Okay. Now I'm going to erase it. You can take a screenshot, pause the video and write it. Okay, you have time. Now I'm going to show you the other method. So very shortest way, directly, without reaching to any of these results. Without reaching to any of these results. From here, directly, what if I can get MC square directly out of it? MC square directly out of it. Then it becomes 3RT, NRT, RT over Mn equals to C square. MC square. MC square. MC square. Right? 3nRT over capital N. So from here, from the equation number 4, from equation 4, have a good look. From equation 4, from here, I need to get, have a good look at this one. It is very important to notice this. From the helplines, from the equation number 4, when you rearrange capital N over simple N over, the capital N over simple N, it just reached to the result 1 over capital N. Okay, again, I am going to substitute this whole thing as 3 RT over L equals to MC to the power 2. Right? Okay. This is like equation 10 from here. I'm going to plug to the equation number 1. And the direct result, you get half what? 3 RT over L. And R over L, before that, 3 R over L is K, 3 KT equals to MC square. This is the direct method. So you can substitute now. So 3 KT is the result. EK is just equals to 3 over 2 KT in a very short way. Very short way. Previous one is also very essential. This one is a very short way. If they ask you to derive and so, easy. Easy. Okay, copy them. Post and copy them. Okay. I'm going to erase. Now you got to know 2 methods to use that. Okay, let me just count. I told you that is the kinetic energy for one molecule. If there are capital N number of molecules there in the sample, the total kinetic energy is capital N multiplied by kinetic energy of one molecule. One molecule I already know the kinetic energy of the total is what? 3 over 2 NKT is the finalized equation. Finalized equation for the kinetic energy. Right? Finalized equation. Okay. Now, this is very important. Very important. Is a dash condition. It's not finalized yet. Now I'm going to, it is like in the previous case, R over L, you just bound them and made Boltzmann constant. It's like marrying 2 people by force. Now earlier you got them married. Now you are going to divorce them forcefully. But now we have to see what is K. It is R over L. Hari amutu physics. This very weird thing is physics. See, then R over L T. Let's see now. Okay. Now see. E total equals to 3 over 2 N over L. Oh, yes. See now, RT. What is N over L? N over L. It is the equation number 5. Very important. That is equation number 5. Is it double dash? 2 is a double dash. I'm going to plug equation number 5 into the equation number. Is a double dash from here. And the equation is just becoming what? E total equals to 3 over 2. N over N is NRT. Something. Is it triple dash? What? NRT? Yeah, which one it is? It is PV. That is PV. That's right. That is PV. Okay. E total you can get in this equation to PV. Very simple and very beautiful physics. And I told you from this equation there is another part. There is another part not belongs to these final results, but there is another separate destination is there. Let's see that one even and copy this by pausing. Look at from this equation. As I told you, PV equals to 1 over 3 m into n. Is for what is m into n? Molecule of mass of one molecule multiplied by number of molecules. That gives you the mass of the sample m naught. Mass of the sample. PV equals to 1 over 3 m naught c to the power, right? Let me just keep P 1 over 3 m naught over V. Mass or volume? Mass or volume. That is none other than density. So it is rho. P equals to 1 over 3 rho c to the power 2. This is also very important result. And c square by we can get it in different, multiple, different way. How? See, P over 3P over rho. Okay. So C bar is 3P over rho square root. Don't you see anything? Something really like this. That is none other than speed of sound in a fluid is speed of sound in, speed of longitudinal waves in a gas. That can technically speed of sound in the air. V is equals to square root of gamma P over 2. In that one, even if the pressure increase, also the density increases. So these two have no significant effort, but don't write it just like 3 because other two are not. No, it is really necessary for further explanations. That's it. Okay. So sometimes we can derive another thing. It is not that much important. When I substitute C squared here, kinetic energy in a separate method, not including temperature now, M what? P over, 3P over rho. Technically, it is just going to be 3 over 2 MP over rho. Not a prominent one, right? Sometimes in an MCQ, they might ask this one. Better to know. This is all about kinetic molecular theory.